Integration of rational functions by partial fractions. So let's start by recalling that a rational function is the quotient of two polynomials. So for example, here's a sum of three rational functions. And I can take these and rewrite them as one rational function by putting them over a common denominator and then simplifying. Now suppose I want to integrate a rational function. Well, the left-hand side of this equation in green is really easy for us to integrate. We know how to do that. But if I had given you the rational function on the right-hand side of that equation in red, that would have been really hard to integrate. In fact, I'm not sure we knew yet how to do this. So here's how we're going to go about doing it. First, we need to remember a little bit about rational functions. So let's set up a rational function f of x, which is p divided by q, where both p and q are polynomials. We're going to say that if the degree of p is less than the degree of q, then f is a proper rational function, and otherwise f is called an improper rational function. Now this is important because what we're going to talk about next is going to depend on f being a proper rational function. So here we're going to learn something called partial fraction decomposition. And to do that, let's remember or learn a few things about polynomials. The first is that if I have a polynomial with real coefficients, I can always factor it down into a set of linear terms times a set of quadratic terms. If the quadratic term can't be factored any further, then it's called irreducible. And then what's really cool is that it can be proved that if you have any proper rational function, you can express it as a sum of terms called partial fractions having the form of a over ax plus b to the k, or bx plus c over ax squared plus bx plus c raised to the k. Now in this, it's important to note that the capital letters and the lowercase letters are distinct. They're not the same. So now let's set up a rational function f of x, which is equal to the polynomial p divided by the polynomial q. What we're going to do is we're going to completely factor the denominator of q of x into linear and irreducible quadratic factors. Once we've done that, we're going to collect all the repeated factors so that q of x is expressed as a product of distinct factors of the form ax plus b to the m and ax squared plus bx plus c to the m, where the quadratic term is irreducible. Right? Then we're going to write p of x over q of x as a sum of other rational functions by doing the following. For all the linear factors of q of x, so the ones that are of the form ax plus b raised to a power, what we're going to do is introduce m terms that are going to look like this. On the top is going to be constants, and they're all distinct. And on the bottom, watch what happens. We have ax plus b, then we increase the power by 1, and we keep doing so until we have m powers of x here. So we're going to end up with n terms. Now what we're going to do is for each of the quadratic factors, and they have to be irreducible, we're going to introduce m terms again, where m is the power of the quadratic factor of the form, and here instead of just a constant in the numerator, we're going to have a linear term of the form ax plus b. All right? And in the denominator, what we're going to do is take that factor and start it with the power of 1, increase the power by 1, and so forth until we have it up to the power of m. So these constants that we're introducing, the capital A's, the capital B's, aren't determined yet. We just know they're going to be there. So now let's do an example and see what we mean by all this, because I know it's kind of vague, but an example should help a lot. Here I have a rational function. And if you look at it, it's got 3 factors raised to some power here, right? So what we're going to do is I'm going to rewrite it using this partial fraction decomposition like this. The x minus 1 term is squared, so I introduce 2 terms On the top I have distinct constants, and then on the bottom I have x minus 1, and then I have x minus 1 squared, and I stop because I've reached the power here matches the power here. Now I'm going to add on terms for the x plus 3. So here's my 3 distinct constants in my numerator, and on the bottom here I have x plus 3 squared, x plus 3 cubed, and I stopped here because now the power here matches the power here. Now for this last term, that's an irreducible quadratic factor, and it's raised to the power 2. So I introduce the 2 terms here, and notice in the numerator they're both linear with distinct constants, and in the denominator I start with my irreducible quadratic factor here to the power 1, and then in my next term it's squared, and I stop here because the power 2 matches the power 2 here. Let's look at another example. This one's of the form 5x plus 4 over x squared times x squared plus 4. And now I have to write this out using the procedure before. Let's start with the x squared. Well, x squared is quadratic, but it's not irreducible because that's equal to 0 when x is equal to 0. So what this really is you need to think of this as a linear term squared. Think of it as x minus 0 squared. So for that, I'm going to add on 2 terms, one for x squared. They're linear, so I only have a constant on the top. And now I add on a term for the x squared plus 4. It's raised to the first power, so there's only one term. Since it's an irreducible quadratic, in the numerator I have a linear term. Okay? So now let's use this to evaluate an integral. Let's evaluate the rational function. Let's evaluate the integral of the rational function 1 over x squared plus x minus 2. So the first thing we're going to do is completely factor the denominator. And now that we've completely factored the denominator, we're going to write it as a sum of partial fractions. So x minus 1 is linear. There's one copy of it, so there'll be one term for that. X plus 2 is linear. There's 1. It's raised to the power 1, so there'll be one term for that. Now what I'm going to do is I'm going to multiply both sides of the equation by x minus 1, x plus 2, the denominator of our rational function, to get this equation here. 1 is equal to a times x plus 2 plus b times x minus 1. Now what we're going to do is solve for a and b. To do that, I'm going to substitute values of x into here to make various terms 0. So the first thing I'm going to do is look at this term here, and I'm going to say to make that term equal to 0, I'm going to plug in x equals 2. Not 2, but negative 2. So when I plug that in, I get that 1 is equal to 0 plus b times negative 3. So that tells me that 1 is equal to negative 3 times b, or that b is equal to negative 1/3. Now we can do the same thing to solve for a. We'll let x equal 1 to make this term go to 0. That gives us that 1 is equal to 3 times a, or that a is equal to 1/3. So this method works nicely. It doesn't always work, so here's another way we could have solved for a and b. We could have taken the equation we got to right here and then set up a system of equations by equating the corresponding coefficients on both sides. So here, if I expand out, I get 1 is equal to ax plus 2 times a plus bx minus b. I collect my like terms, so here's the terms that have an x, here's my terms that are constant, and I've rewritten the left-hand side of the equation as 0x plus 1. So that's going to tell me that a plus b, the coefficient of x, has to equal the coefficient of x over here, which is 0, and that the constant term 1 has to equal the constant term on the right-hand side, which is 2a minus b. So now we end up with a system of equations you can solve this system of equations to get that a is equal to 1/3 and b is equal to -1/3. All right, so we just found values for a and b, so we go ahead and put them back into this equation. And now we've done our partial fraction decomposition for our rational function. So now we can go ahead and integrate. We can now say that the integral of 1 over x minus 1 times x plus 2 is equal to the integral of 1/3 times 1 over x minus 1 minus 1/3 times the integral of 1 over x plus 2. Both of those we know how to integrate, and we have our answer. This was a fine answer here, but here we have a difference of logs. We can use our properties of logarithms to combine them into one logarithm, and that answer's a little bit nicer. So that's where we'll end. All right, that wasn't too bad. Let's do another one. Let's do this one. Here we have 3x to the 4th plus 3 times x cubed minus 5x squared plus x minus 1 being divided by x squared plus x minus 2. And this is a great rational function. The only problem is it's an improper rational function. Notice that the degree of the numerator is 4 and the degree of the denominator is 2. So I can't jump right into doing my partial fraction decomposition. When this happens, when we have an improper rational function, we have to use long division of polynomials to rewrite our rational function as the sum of a polynomial and a proper rational function. So if you perform long division polynomials on our rational function, you'll get that it's equal to 3x squared plus 1 plus a rational function 1 over x squared plus x minus 2. So now we can go ahead and integrate. This integral is going to be equal to the integral of our polynomial plus the integral of our little proper rational function 1 over x squared plus x minus 2. Now, this integral right here, we've already seen. We did this in example 2. So we can use those results to get that this integral here is equal to the antiderivative of 3x squared plus 1, which is x cubed plus x, plus the antiderivative of 1 over x squared plus x minus 2, which from example 2 we saw was this piece right here. And that gives us our final answer.